students and staffs and imbibing their work culture and learning in European standards. During this time, he has traveled extensively in African continent to learn and share views about internationalization of medical education. He was appointed as a research director at Department Dean University Colombo in January 2016. He continues now as a dean of Department Medical College, which he took over in June 2016. He is a very keen researcher and enthusiastic personality, presently working with us on angiogenesis and reversal of angiogenesis in endometrial stem cells as well as cervical stem cells, collaborated with the Department of Stem Cell and Regenerative Medicine, Department University, using in vivo and in vitro studies, CAM-assay models. He is also a university approved guide for PhD students. He is an active member of various professional and philanthropic bodies. He has published several national and international journals. He has co-authored the book in research methodology. He has been a member of Independent Ethics Committee for Research on Human Beings MOFI from the year 1998 to 2012. He was involved in the review, clearance and monitoring of over 200 clinical research projects undertaken by various national and multinational institutes. He has served and invited members and experts on the Service Selection Board of Madhya Pradesh. I warmly welcome you, sir, over to R.K. Sharma, sir, to start the technical session. Thank you.
Good morning, everybody.
आप इधर से आ जाओ ना।
So also I would like to thank the UIR University and the organizing committee for giving me this opportunity to join the session, in which two of the very eminent speakers are going to speak. So, I think without any ado, I would like to introduce the first speaker of the day, Professor Rudolf, who I think we have here on the stage in the morning. He received his PhD in 1983 from the University of Bonn, Germany. Afterwards, he joined Professor E.B. Yeager at the Case Center for Electromedical Sciences, Case Western Reserve University, Cleveland, USA, as a postdoctoral fellow, and then Oldenburg University in 1987 as associate professor in physical chemistry. Since 1993, he is full professor of physical chemistry and electrochemistry at the chemistry department of Technical University, Chemnitz, Germany. His research is focused on spectroelectrochemistry, self-assembled boron layer, lithium-ion batteries, electrochemical energy conversion and storage, electrochemical material science and production. He is an honorary member of Secretary Academy of Sciences and of several editorials. He is the author of more than 370 articles in referred international journals and 11 books. Dr. Holz, I invite you on the stage to talk about your talk is on pseudo-capacitive or not, on the origin of current in supercapacitor material. Please welcome.
Thank you very much. That was excellent. And also thank you very much for the kind invitation to attend this conference and to speak at this occasion. Talking about merger, which is now displaced, well, it would be better because I tend to move around. Getting back to the type of conference about merger, the subject I'm talking about, well, maybe not just from the title, it's also about some merger. It's about the merger of batteries and supercapacitors. I assume that maybe not everybody in the audience is familiar with all details of this, major details of supercapacitors in particular. And those aspects I'm talking about in the next few minutes. So those experts like Dipak Duval or Chandra Alexander might just for a minute tolerate some broader introduction to provide some background for those of you who are not yet familiar with supercapacitors and this merger I just mentioned. If you want to store electric energy, you can store electric energy only by means of various transformation processes. Either by transforming electric energy into chemical energy, that's what we are doing in electrolysis, that's what we are doing in batteries, when we charge a battery. There is one exception: you can store electric energy in capacitors without any transformation. That's very welcome, because any transformation, we cannot generate energy, we cannot destroy energy, we can only transform energy. Every transformation of energy of one form into another form is associated with losses. Whether it's the transformation of the energy stored in crude oil or stored in nuclear or whatever energy into thermal energy, into electric energy in a power station, or whether it's the conversion of chemical energy stored in gasoline into mechanical energy, it is always associated with losses. A few percent, or a few 10%, or even worse. So any storage process without conversion is highly welcome, and that's the reason why capacitors are basically so attractive. On top of this, in recent years, there are two more interesting and more important aspects. One aspect, if we try, and India is trying the same, like all of Europe, China, and so on, if we try to integrate renewable energy sources like wind, like photovoltaic, into our energy landscape, into our daily use of energy, these energy sources like wind or photovoltaics are variable, they are fluctuating. So we need to match supply, sunshine, also flowing wind, with the demand. And this requires an improved grid structure. It also requires storage. Beyond this storage, which is related to the integration of renewable energy sources, we also would like to utilize energy more efficiently. So, for example, if you run an electric train in the subway, you would like to utilize the mechanical energy in the train when you are going to brake. The same applies to every car. This so-called regenerative braking is highly efficient. It can reduce the overall energy usage or consumption of a bus by 30 or more %, which shows up very nicely in the balance sheet, in the cost of running such a bus. In order to store or to regenerate this energy, you need storage devices which are capable of taking up the electric energy generated when the train or when the bus is braking. The huge electric power generated in that very moment when the train is braking cannot be accepted by any known battery. You might have heard, well, you can do it with lithium-ion batteries, but that is rather unrealistic. So we need devices which can take up electric energy, electric current in particular, at a very high rate. And once again, capacitors come into play. The traditional capacitor, the capacitor you might remember from physics lectures at school or first semester at the university, just a plate and some insulator in between, is a very nice capacitor, but in terms of storage capability, it is very poor. So it is of almost no real use in this energy landscape which I just outlined. And only a few years, actually by now a few decades back, it was noticed that you can use the so-called electrochemical double layer. That's the interface between an electrolyte solution, just take a solution of salt and water, and an electronically conducting material, just take a piece of carbon, activated carbon, whatever. This interface behaves like a capacitor, and since this interface area can be made very large, if we take, instead of a simple piece of graphite, we take a porous body, a compressed body, let's say, of activated carbon powder, then we get very large interfacial surfaces, and accordingly we get also very large capacities. And if you take two such interfaces and connect them in series, you have a so-called double layer capacitor, or electrochemical double layer capacitor. And these devices have been called many years ago, it's still not quite clear who coined the term, supercapacitors. These are just capacitors with a very large capacity as compared to this device from the physics lecture with these two metal plates. But even these supercapacitors, in terms of their energy storage capability, are not satisfied. We would like to put even more energy into even smaller devices. And at this point, supercapacitors start to merge with batteries, because those materials which we are interested in, and those materials I'm going to talk about within the next few minutes, are materials where the electrical energy is not simply stored in the double layer, at this interface between ionically conducting electrolyte solution and electronically conducting porous carbon material, but the energy is also stored in superficial redox processes. In redox processes where ions like manganese or some other metals, as you will see in a minute, on the surface of the electronically conducting material change their state of oxidation. Manganese from +4 to manganese +3 and so on. This way, the amount of stored electrical energy in a given device or on a given surface area of 1 square centimeter or 100 square meters or whatever can be increased, can be enhanced by a factor of 10 or even 100. And because now we do not simply employ the separation of charges like in the double layer capacitor, but we also employ redox processes, these materials have some very promising future, hopefully, but they have also come under scrutiny regarding the question, what is really happening at this interface? Maybe it's not just simply a redox process, as we have known from many other phenomena like corrosion or fuel cell reactions and so on. And what is the reason why these capacitive currents or these electrode responses of such a supercapacitor electrode look so much different from the behavior of many other electrochemical systems, of many other electrodes? Just to give you an example, because right now, so far, the last 3 minutes might have sounded rather abstract or rather theoretical. This is the so-called cyclical thermogram. That's the response of such an interface between a piece of metal, gold, and an electrolyte solution composed of perchloric acid, protons, and perchlorate ions in water. If we change the electrode potential of this arrangement, the gold metal in this electrolyte solution, if we change the electrode potential into the positive direction, we observe a very small flow of current, which is simply due to the fact that we are storing electric energy in this double layer. Because when going into positive direction, we change the distribution of positively charged cations, the protons, and negatively charged anions in the solution, and we remove electrons from the gold because of moving into the positive direction. And the current response, as you can easily see with your own eyes, is basically flat, and the current is small. If we change the rate of potential change, if we do it faster or more slowly, the current response changes a little bit, and you can see it much better in this case. The current response as a function of the scan rate changes in a linear fashion. And this relationship is typical of the capacitor. For that reason, this range of electrode potentials has been called the capacitive range or the capacitive behavior. This electrochemical interface behaves like this capacitor, two plates, and an insulator in between. If we move to more positive electrode potentials, the currents suddenly become much larger. Once again, as a function of scan rate, I have displayed the currents, and now the currents are larger by about 2 orders of magnitude. You remember? In these supercapacitor electrode materials, in electrodes and cells, we can store about 10 or 100 times the amount we can store if we just employ the double layer capacity. And once again, the current increases as a function of the scan rate in a linear fashion. When we are looking here, and when we are looking here. What is going on in this range? In this range, we are oxidizing water and gold, and we form a layer of gold hydroxide on the gold surface. And this gold hydroxide is slowly turned into gold oxide, and finally, when we go on, we will make oxygen by oxidizing water. When we go back, we reduce this oxide or gold hydroxide layer, and once again, in this range, we are in the region of pure double layer charging. So both this capacitive current as well as this current, which is due to some redox process, look like capacitive. But since we know this current, this much larger current, is due to a redox process, this process or this behavior, this appearance, this linear relationship has been called by Brian Conway and co-workers pseudo-capacitive. Okay, so far so good, and now I think everybody in this room will ask me or himself, is this guy really talking about a supercapacitor made of gold? No, not at all. I just took gold as an example to make the distinction between the capacitive and the pseudo-capacitive, because the current response, as seen in this picture, behaves like a capacitive process, but in reality it is not a capacitive. It is a redox process, but it behaves in terms of the current response like a capacitor, and that's the reason why it is called pseudo-capacitor. Now we move to some more realistic material, which, for example, is manganese dioxide. Manganese dioxide, much cheaper, environmentally acceptable, and so on and so on. And in this example, we have coated, just for an illustration, we have coated manganese dioxide on a piece of graphite. It's very smooth surface. We have coated the manganese dioxide on a stainless steel sheet. The use of stainless steel goes in sheets and in nets has been introduced into our group by Deepak Dubal when he was a Humboldt Fellow in our group a few years ago. And we have coated the manganese dioxide onto a stainless steel net. Once again, I could make such a plot which would look exactly this way, and the response, it's not rectangular, but it is very close to a rectangle. The response of this material is like the response of a capacitor. Although we all know in this room, it is due, this current response is due to the change of the manganese 4 to the manganese 3 ion when we go this direction, or when we go this direction, the manganese 3 into the manganese 4. And only at this point you see a small, oblique wave, and such a current wave, or more precisely a current peak, we would expect from a redox process. The question, and that's the title of this talk, why does this current peak almost completely disappear and only such a current response, I even would not call this a current wave, I just call it a current response, results. The reason for this is so far barely discussed and I'm afraid also barely understood. So what is going on at this interface? Well, I talked about it already. At the interface, the electron transport, metal is an electronic conductor, whether it's the gold, or whether it's the stainless steel, or whether it's even the graphite, where there are mobile electrons inside. So when we are moving into the positive direction, electrons are removed from the graphite, from the stainless steel, and so on. Something is oxidized, and as I told you a minute ago, the gold is oxidized, or the manganese 3 ion is oxidized, and for charge compensation, anions from the electrolyte solutions, anions like the sulfide anions in this electrolyte solution, it was an electrolyte solution of sulfate in water is moving towards the interface. So these are the species in solution. This is what's going on at the interface. But why is the current response so much different depending whether we are observing a redox process in a traditional cyclical thermogram, where such a wave is not only a wave but a very pronounced peak, and why in the present case it is just such a shape. Well, this is a very early example reported by Brian Conway and W. Pell. It's the ruthenium oxide. And once again, you see not exactly a rectangle, but you see an almost rectangular response and very weak waves on it. The assignment, the interpretation, what is going on, has been given by Conway. It's the change of the redox state of oxidation of the ruthenium, and the ruthenium has various states of oxidation, so the electrochemistry is a little bit more complicated, and these waves, I would not call it a peak, these waves are somehow associated with ruthenium 3, 4, 5, 6, and so on. But why is there such a huge current under these very weak waves? Well, in case of the manganese dioxide, basically the same argument has been proposed. I already mentioned in passing. We are oxidizing the manganese 3 into the manganese 4, and what is going on for charge compensation? Well, first of all, we have the anions from the electrolyte solution, and also authors have claimed, well, the sodium ions are moving in for charge compensation, so some people talk about supercapacitive behavior of electrode materials in terms of ion absorption. But why is the oxidation of the manganese 3 into manganese 4, or of ruthenium, I don't know, 4 into 5, whatever the number we have picked, why is this response not showing up as a current peak, but in this particular shape? Well, just as a reminder, this is a picture you would get if you would do exactly the same experiment with a capacitor. In this case, with an electrolytic capacitor. You get a constant current, no peaks, because in such an electrolytic capacitor, you only have aluminum in contact with an electrolyte solution. The technical details of a capacitor I should not discuss here, and this is only a detail of the electronics of the potentiostat. It's not related to the behavior of a capacitor. So why is such behavior observed with a capacitor? A similar pseudo behavior is observed with manganese dioxide, although the underlying processes are totally different. Well, as a criterion to identify a process as being pseudo-capacitive, you can either take this kind of shape, or if you do a constant charge-discharge experiment, this kind of voltage response. In experimental electrochemistry, frequently investigators charge or discharge, oxidize or reduce materials at a constant current or constant current density. And if you charge or discharge a capacitor at a constant current, as has been done in this example, with again the same capacitor as used here, this is charging at a constantly changed electrode potential, or in this case